Okay, thanks for the introduction. It's my pleasure today to come to Disney Research and talk about my work on user-centered cross-device interaction. I'm currently a final year PhD student in the HCI Institute at CMU, working with Scott Hudson and Darren Goros. Before I start my talk, I want to give thanks to all my awesome collaborators. Without any of their effort and help, none of the foreign projects would have been possible. My general research area is human-computer interaction, or HCI, and HCI is dealing with problems between the users and digital information. The current status of HCI is that users and information interact pretty much through a small piece of screen, a screen on your phone, or your watch, or your tablet computers, whereby the information is displayed as digital pixels, and users use very simple touch or type interaction to interact with these pixels. So in the past, my research has been focusing on expanding this bandwidth between the user and information, trying to go beyond the simplistic touch and type interaction. And to do that, I take a technical approach. I try to innovate user interface designs by building interactive systems over various kinds of devices. In the past, I've worked with stylus and tablet computers, to wearable devices, to mobile computers, to appliances, and to even the more recently emergent fabrication machines such as 3D printers. So before I talk about the core of this presentation about cross-device interaction, I want to go through quickly, flashing backward some of these projects I've done with individual devices. Smartwatches. This is a text entry technique for users to type on tiny screen on a watch, which they can achieve for as fast as 32 words per minute. Mobile phones. To extend interaction beyond the screen, we can mount a depth camera on top of the phone, which can see the user's finger moving on top of above the screen. So again, enable interaction such as cycling the finger to zoom in the map, or lifting the finger high up to switch between zooming the map versus panning it. And we can also think about audio. So this is a pair of headphones that can detect when they are being removed from the ears. And this is done by emitting and receiving a human inaudible source of sound. So we can do interactions such as pausing the music when the headphones are removed and resuming it when they are put back. Appliances. To interact with, for example, this printer, simply take a picture of it, which connects the printer to the user's phone, renders a user interface for users to directly print something on this very printer from their phone. You can also think about a new class of machines, fabrication machines such as 3D printers. And my work has been focusing on customizing the printing process. So this project allows you to pause the print in the middle and then insert the object. And then when it's finished, the two objects are naturally interlocked together without using any adhesives or fasteners. We can also print a charm bracelet by, in the middle of the print, inserting the charm. And the previously shown simulation ensures that this insertion doesn't impede the subsequent printing of the bracelet. By customizing the printing process, we can also go beyond the default plastic of 3D printing objects. In this project, we're able to print soft structures, which is very important for objects such as this toy horse. So I've shown you some of the previous projects I worked on individual devices. And in this talk, I want to kind of go beyond this level and try to think about how to design and build interactions across devices. In particular, I'm looking at user-centered cross-device interaction. What I mean by this is, by orchestrating interaction across devices, we can capture rich information about users' behavior, intent, and context, thus enabling new interactive experiences that is not possible previously with just looking at devices alone. So I'll talk about this topic in 3 detailed projects. In the first project, I looked at the cross-device interaction between a stylus and a tablet. So we all know that sketching is a very rich and expressive physical activity. Artists use different paintbrush, posture, pressure, or angle, or speed to create different effects. Even for non-artists, such as knowledge workers, we like to use gestures and motions in tandem with sketching to communicate ideas with each other. However, when it comes to digital sketching, it becomes much simpler than the physical equivalents, simply boiling down the sketching activity to simple x and y coordinates. So simple x and y coordinates really cannot capture the rich activities and nuances of sketching. So in this project, I look at a cross-device approach, trying to correlate certain information and sensors information between the tablet and stylus to capture such rich information about the user. So the first step, we need to upgrade the stylus that already tells us the x and y coordinates. And in particular, I try to enhance this stylus with IMU, or inertial measurement unit, a type of sensor that can sense the motion of the object it's attached to. So in HCI, one typical approach is to do rapid prototyping to approximate the kind of future devices we want to have. So in this case, I have a traditional stylus from Wacom, and I have a piece of IMU from Fidgets. And I took a clip from the mailroom, then I just simply hooked up these things together, and then I have a sensor-enhanced stylus. And it can quickly allow me to explore different interaction techniques, from levering, tilting, rolling, hitting the pen, the finger, tapping the pen's barrel, holding the pen vertical, or bumping the pen on the screen. So amongst these explorations, something that's really interesting came to me, which is we can enable interactions such as splattering ink on a digital canvas by hitting the stylus on the user's finger, which really mimics the way artists creatively use paintbrush in the physical world. And you probably also noticed that in this video, I already also upgraded the stylus. We, working with the hardware lab in Microsoft Research, we're able to build this circuit board that contains a 9-axis inertial sensor, a radio module, and a battery, all fit into the form factor of a stylus. So let's look a little bit closer to the implementation of this ink splattering technique. So the key idea is to correlate the sensors between a stylus and the touch events on the tablet computers. So it starts with users touching down on the screen and holding it. And we wait for a delta t time window to ensure that the user is actually doing the touch and hold gesture. And this is by looking at accumulation of the x and y offset. And if it's actually a touch and hold, then look at the stylus accelerometer signal, trying to match the pattern to a predefined hitting the finger pattern. If these 2 conditions are met, we start interaction of spattering ink. In particular, we track the position of the finger's touch position, P, and then I look at the magnitude as well as the number of peaks per second, which directly translate to how hard the user is hitting the finger with the pen and how frequent that hitting motion is. So taking all these observations, create splattered ink pattern at the touch position P as a function of A and N. So we can use A and N to vary the radius of the splattering region, the radii of each ink dot, as well as the number of these ink dots. And the interaction ends as soon as the user's finger leaves the screen. So there is a kind of usability problem in this implementation. Can you see what problem it is? It's this delta t. So the problem is having to wait for such delta t makes the users consider the interface as not so responsive. So it has the potential of lowering the user experience. However, we really need to observe a certain time window to ensure that it's actually an ink spattering action to avoid false positives. Of course, this comes at the trade-off creates latency that lowers user experience. So to solve this problem, I look at two delta t's. So the first delta t1, it ensures us to make a quick decision to make sure the system appears to be responsive to the users. So when we detect an ink spattering pattern at delta t1, we immediately start the interaction. Of course, this might be wrong because we are making a decision very fast. So we log these ink spattering events, and then at delta t2, when we're sure that we have enough observation, we make the detection again. So now if it's actually ink spattering is fine, just continue. If it's not, we can go back to the stack of events and pop and undo all these errors we made. So in this way, we ensure the system is responsive to the users while providing a chance to correct the error if there's any. And we can apply this similar motion or sensor correlation idea for other user behavior, such as accidentally or unintentionally resting the palm on the screen. And this is achieved by looking at the correlation between the accelerometer signal as well as the occurrence of the touch event. So as the palm is resting on the screen, you can see a synchronized accelerometer reading happening from the pen. So this is very different as opposed to touching the screen using the hand that's not holding the pen. So in this project, by correlating motion signals from the stylus and the touch events from the tablet, I show that we can capture users' physical activities such as spattering ink, as well as behaviors such as doing the palm rejection to avoid accidentally creating touch interaction on the screen. So this project also looks at stylus simply as a very specific accessory. And I try to go beyond this kind of notion, and instead, in the next project, I will try to extend cross-device interaction to other smart devices, such as your smartphone and a smartwatch. And it's really a timely question to ask about how we can interact with multiple smart devices. And this picture shows how many more devices we are having between the two Pope inauguration ceremonies, just 8 years apart. And we are really having kind of explosion of smart devices, probably too many for us to really make good use of them. And of course, each device, admittedly, is very smart as individuals. However, the question really is how can we use them collectively to make them also intelligent as a whole. So I look at a very specific combination of two types of smart devices, the phone and the watch, to explore this larger problem. And the main contribution of this next project is a conceptual model that describes how we can design the device-to-device interaction. I'm going to show you this conceptual model up front. So we can see it's a 2x2 design space in which the phone and the watch permeate between the foreground and the background of interaction. And foreground interaction means users are intentionally interacting with the device, such as the simple touching, poking the screen. And background interaction means users are not intentionally using the device, however, the device is still functioning as part of interaction, such as you rotate your phone, the content of the screen automatically rotates with you. So the users do not ask this content to rotate, but just automatically adjust to the orientation of the posture. So by describing the phone to watch interaction in this way, we can really capture the existing approach of how industry and manufacturers design interaction between these two devices. So you can see in this quadrant, with the phone in the background, such as a pocket or backpack, the watch is used as information viewport or remote control. And in the other quadrant, when both devices are in the background, we use them for activity sensing, such as counting how many steps you have in one day. So these point to some directions and previously not explored, which is when the phone is in the foreground and how should the watch function as well as an interaction element. So first I look at both devices in the foreground. And this shows example interaction scenario. The user touch at a map location with cluttered these location markers, and the watch zooms in the area, shows these markers in details, and allow users to zoom in and interact with that particular area. And this is another example of the phone being a display of the primary apps, and the watch is used for multitasking. And then also an underexplored quadrant in this design space is using the watch in the background where users are actively interacting with the phone. So this can be described as, for example, using the watch to do handiness sensing. So by correlating the watch motion signal as well as the hand's touch event on the phone, we can detect which of user's hand is touching the screen. We can also detect different hand parts, such as using the pad, the side, or the knuckle of the finger to touch the screen by looking at the watch orientation together with the touch events on the phone. And so we can do something like using knuckle to move the apps around, and using a normal finger pad to open an app. So such hand part detection is achieved by associating the watch orientation with the touching hand parts. As shown in this figure, you can see the watch orientation is very distinctive between touching using the pad, the side, and the knuckle. However, there's also a problem in this approach. So the problem is we don't hold a phone in a fixed orientation. Sometimes we might be looking down, looking in front of us, or even just lying down and then holding the phone sideways. So it's not going to work if we just hardcode the watch orientation. So to solve all these different cases, I take a more data-driven approach. So I develop features collected from users holding the two devices at different postures and orientations. So the first important feature, of course, is the relative orientation between the two devices. And this is computed as the mean accelerometer reading at a static space in the time window t before the touchdown.
Sorry, what's t?
T is the time window before the touch happens. Yeah. I also look at impact, which is how hard the hand part is landing down on the screen, and also the direction of such impact. I also looked at motion profile, which is a larger picture of how the sequence of motion is behaving before and after the touch event. So imagine when using the knuckle to touch on the screen, the user might start from flipping the hand, landing down the knuckle, lifting the finger, and then flipping back. So by looking at this entire motion profile, you can also describe this kind of gesture in a more distinctive way. So taking these features, I use the AdaBoost method with decision tree for machine learning model training. So for this particular technique, as well as the other interaction technique, I perform 3 passes of evaluation. So in the first pass, I look at the overall performance, in which I perform a tenfold cross-validation across all the data collected from all the users. In the second pass, I look at each user individually. Again, I perform the cross-validation for each individual user, and then aggregate the results across them. And finally, I take a more general approach in which I hold out one user's data each time as test set and use the rest as training set, and then repeat this process for each user, and then aggregate results. And this table shows the performance using these 3 passes of the evaluation. So we can see, using to evaluate the robustness of certain technique. For example, this double bump that involves bumping the watch using the phone twice is not working as well as the others. And as we observe, it actually coincides with a lot of other hand motions. So imagine I'm holding a phone and I'm moving as I speak, then sometimes we might have a similar pattern that will confuse recognition of this technique. So false positive cause performance downgrade of this technique. We can also compare techniques that might look similar in performance. For example, flip and tap, which involves flipping the hand and then tapping on the screen, versus hold and flap, which means holding the phone and then flip it and then back. So these two techniques have similar performance at the 10 and the overall level. But when it comes to individual users and cross users, we can see that the hold and flip, the performance of hold and flip drops quite significantly. And as I investigated into the process, I found that users tend to perform hold and flip quite inconsistently. So this caused some kind of variance and low performance. And also users tend to perform this technique differently across each other, which also explains why it has low performance compared to the other one. So together, by performing these three passes of evaluation, we can really compare different techniques and look at how well they perform at a general level, at each individual user or cross users. So this is the second project in which I look at the phone and the watch to jointly create and support interactive tasks for the users. And this is achieved by having the devices take on different roles in the foreground and background of interaction. And the main contribution is the conceptual model that described both existing approaches as well as the new directions that can create new experiences by having the two devices, the phone and watch, work together. And so a little bit more about this conceptual model is actually inspired by research in behavioral linguistics. So researchers, by observing how people talk to each other, found that in conversations that involve two or three or more people, two of them might actually jointly carry out a certain conversation, such as a couple telling you their weekend story of a trip. But from a third listener, it sounds like these two couple conversation is actually a single story coming from a single speaker. So that was kind of the design goal of this project. I want to have the two devices take turns, take on different roles, working together in a way that, from the user's perspective, it looks like it's one unified interactive platform that's working for them. And this idea also resonates back to the first project in which I have the stylus and the tablet computers jointly to detect this interaction of spattering ink by hitting the stylus on the finger. And again, these two devices are taking on different roles in a way that for the users, it's one single unified interaction technique. So then, after these two projects, I started to ask more questions. So looking at this combination between the phone and the watch seems interesting. However, it doesn't seem very scalable, looking at how many other devices we have. So I continued exploration. So I take a kind of different approach. Instead of designing and building interaction on my own, I try to enable users to define and program cross-device interaction by demonstration. So this is really a pressing issue because in the future, we're gonna have more devices in a more connected way. So for each device, traditionally we have the input and output centered on one single device. But now as we have more of them connected, these input and output are actually distributed across devices. For example, as I'm giving this presentation, maybe what I can do is I can control the slides from my phone, or the audience can use a tablet computer to take notes, or can use gesture to control the slides, or I can even create VR experience. To make all this possible, we currently already need to build these platform-specific apps. We need to have an app that runs on a phone, that connects to a laptop, something runs on a watch, that connects to a tablet, etc. So the problem is, it's a lot of work considering how many devices we have. Developers need to build this and maintain these platform-specific apps. And users need to install and learn these new apps in order to control a new IoT device or a new application. So in this third project, my goal is to come up with one app that lets users control various native applications of IoT devices. So I built a framework called Improv that lets users improvised interaction between devices. So for example, let's say now I really want to control my slide, not pressing the keyboard, but using my phone. However, I don't have any app pre-installed on my phone to connect it to my laptop. So how can I do that? So I built this framework that lets users demonstrate how they want to use these devices together, such as using the two-finger tap to go to the next slide. So to program this interaction, users first demonstrate the go to next slide action on the application and then perform the two-finger tap on their phone. And that's it. The underlying framework makes the association, and then the user can already have the gesture they created run in real time. And they can also create another gesture for going to the previous slide, or a continuous gesture to control the slide deck. Or even motion gesture. Or using the touch screen of the phone as a pointer. So again, all of these interactions are not pre-programmed, but rather defined by the users at runtime by demonstration and depending on the particular interaction scenario that works for them. So this framework called improv enables such improvised cross-device interaction defined and programmed by the users. It works with real web apps. So this is Pandora. User creates volume control on the phone. And this SlideShare for navigating slides using gestures. And this is Custom Ink, a t-shirt design website. So improv is implemented as a Chrome extension that works with real web apps, as shown in the previous video. The user can see a list of connected devices. They can click this plus button to create a new improvised input or a new improv. So each improv is displayed first as a gesture that's happening on other devices. And once the user select this gesture and click the play button, they can replay what this particular cross-device gesture is going to cause the application to do. They can also turn on and off an improv or delete them. They can also adjust the CD gain ratio, which is how sensitive the application is going to react to a certain gesture. So under the hood, what's happened is that improv maps user-defined input from one device to the output on another device application by ways of matching their degree of freedom. So degree of freedom is something I define here that's really the key of implementation. So first, UI behaviors or output. So remember that now we're talking about input and output on separate devices. So regardless, UI behaviors output can be characterized by degree of freedom. And let me explain what this means. So for degree of freedom 0, we have clicking buttons or selecting items from a list. So these are discrete actions happening to a particular interaction element. For DOF1, we have dragging sliders or resizing a shape. So this means that the behavior of this UI can be characterized by a linear motion, whereas X and Y coordinates can be governed by linear functions. So this is DOF1 with linear correlation. Another type of DOF1 is rotational correlation, such as rotating a dial or turning a knob, in which X and Y coordinates are governed by a rotational correlation model, such as an angle. And finally, when there is no correlation, such as sketching, we have degree of freedom 2, in which X and Y both are free to move to any place on the screen. So knowing there is these three types of degrees of freedom, improv can then extract such degree of freedom simply from the raw UI events, which means it doesn't need to modify the source code of a web application, but just by observing the UI events, they can extract this information. So assuming we have an incoming touch or mouse movements, so first we compute the footprint, which is how much the finger or the mouse moves during the course of this action. And if it's smaller than threshold, then we consider it as a DOF0 action. Otherwise, we look at whether it's degree of freedom 1 or 2. So determining that, first we try to fit the coordinates to a circle, as well as trying to fit it to a line. So in the case of circle, we look at the error of the fitting. It's not enough to look at whether the error is smaller than threshold, because theoretically, an infinitely large circle can fit to even a straight line. So we also look at heuristics, such as the center of this fitting circle needs to be within the bound of the screen, and the radius needs to be smaller than a certain portion of the screen size. So having these three conditions can ensure that we can capture UI behavior, such as rotating the knob or turning the dial, which is DOF1 with the rotational correlation. And if it's not rotational, then and it fits to a line, then it's linear correlation, again, DOF1. And then finally, it's DOF2, if none of these is satisfied. Okay, so at an architectural level, users start with demonstrating something on the application on one device by actually performing the interaction, in which the framework logs the raw UI events, interpret the degree of freedom, and then create a UI behavior model. So, and then it's gonna store such information in the improv library. So that's the half of the equation for demonstrating a cross-device input. And for the second half, the user is gonna go to some other devices and demonstrate the input. And again, input can be parameterized by degree of freedom, knowing that what DOF is already taking place by the output. So let's say a user is performing a left bracket gesture on the phone. So if we already interpret DOF is 0, then we treat this entire input as a gesture. If it is DOF1, then we can either try to fit it to a polyline in which measure the length, or we can try to fit it to a circle in which measure the angle. So both give one variable because it's DOF1. And if on the output side it's DOF2, then we simply take x and y coordinates without assuming whether it's a symbol, a line, or a circle. So all these extracted symbol, length, angle, or coordinates are called properties. So at system level, now the users have gone to other devices. They have demonstrated what input will cause the previous output. So then we're done for the demonstration. And then they can go ahead and use what they already created. So at runtime, users start by issuing some sort of input. So first, it's important that we use the user's input to retrieve the type of UI behavior from the improv library. And once it's retrieved, we extract properties, taking their values, feed them into the mapping function from the UI behavior model, also from the library. And then what we do next is very important. We generate events again that are dispatched to the application to simulate what the users desire to happen. And I'm going to explain what this process in more details. So we then simulate raw UI events. So if it's DOF0, such as clicking a button, we simply replay the logged events. So the same button we click again. If it's DOF1, such as dragging a slider, then we generate X and Y input with linear or rotational mapping functions. So if it's a linear correlation model, both X and Y can be governed by a linear function, in which case MT could be a governing variable extracted from the property of the user's input. And if it's rotational, we can fit it to a rotational model, in which the angle becomes the governing factor. And with DLF2, we simply map x and y coordinates from one device to the application side, times the CD gain ratio that can adjust the sensitivity of this mapping. So that's the overall architecture of the improv framework. Importantly, users only need to take 2 steps, demonstrating what's going to happen on the application and the corresponding input. And then the system, this pipeline, makes underlying association. Improv is implemented as a Chrome extension where raw UI events are logged and simulated using JavaScript. And the companion apps can run on various kinds of platforms on Android based on phones, watches, tablets, etc. And by enabling user-defined cross-device input, we can really explore different application scenarios. So first, I want to show how the same type of output can be caused by different user-defined input. So this is a rotating a knob. So this is very intuitive mapping. User can also use 2 hands, or use a linear motion, or 2-finger linear motion, or even 2-finger pinch and zoom, all performing the same type of action. And using improv, we can optimize input modalities. So if dragging a small handle on this picture is not ideal, we can appropriate a phone screen to do direct pinch to zoom. We can also encourage collaboration. So if 2 users are sharing a laptop, for example, one can take out the phone and then create an improv, and they can both use the same application without fighting over the control of this laptop. We can also mitigate situational impairment. So when cooking is not convenient to access the laptop, so it's important for users to, in this case, improvising a watch flipping gesture to pause and play the cooking video. We can also create cross-device macros. So if certain interactions are too tedious to perform, we can chunk these actions as one single gesture. So in this case, this painting application, switching between different painting styles can be achieved by a single gesture performed on the phone. And again, all these can be created and customized by the users based on their particular preference. We perform the user evaluation of improv. So there are 2 parts. In the first part of the evaluation, we evaluate the accuracy of interpreting UI behavior, looking at the degree of freedom interpretation. In the second part, users experience the real application scenarios and rate the usefulness and ease of use. And quickly, here's a table of all the tasks in the study and the demographic information of our participants. So the key finding is that in interpreting the degree of freedom, improv achieved 93.7% accuracy from just one single example of the raw events.
So this means interpret the degree of freedom or interpret the behavior, interpret the gesture?
Both. So for first, interprets degree of freedom. So for degree of freedom 1, there are 2 correlation models. You also interpret the rotational linear. So it needs to be correctly mapped, degree of freedom and correlation.
So how many gestures are there in each degree of freedom? For example, for degree freedom 1, how many gestures are there?
You mean how many types of UI widgets?
Yes, yeah.
We have horizontal slider, vertical slider, diagonal slider, and also resizing a shape.
But how do people choose the slider among all the UI elements?
Well, they have to go through different kinds of UI elements. So we try to exhaust different types of linear motion on the UI, from horizontal to vertical to diagonal.
Yep.
Okay, so on average, it also took a participant only 10 seconds to create a cross-device input technique. So this really shows how improv can be used even at a very immediate scenario, such as giving this presentation. And in terms of user feedback, most users don't have trouble learning and performing the process. They also like the flexibility of customizing input and output across devices, also saw usefulness in specific application scenarios. But what's interesting is the most other feedback, such as some people have trouble coming up with gestures, and some people might have trouble creating gestures that are actually usable, which really tells us that although we can give users the capability of creating interaction, they are, at the end of the day, not interaction designers. So for the future world, it's really important to inform and provide users with the guidance of what gestures are possible and how to correct certain usability problems. So that's improv, is a user-defined cross-device framework for demonstrating to create interaction, which empowers end users to easily customize how devices should work together. So in the past 3 projects, I can see that we can correlate different devices' sensors to enable rich behavior, such as spattering ink, to detect meaningful context, such as palm rejection or handedness, or to recognize nuance intents, such as using different hand parts. We can also learn from users' behavior to design cross-device interaction. And in the phone and watch project, we design multiple devices to take turns to interact with users, yielding a 2x2 foreground-background design space that guides how such interaction should be designed across devices. We can also support a wide range of user activities, intents, and behaviors by giving users the capability to improvise cross-device interaction based on their own preference and the interaction scenario. And all this can be achieved by simply demonstrating what they want without doing any programming. So together, I consider this body of work user-centered cross-device interaction, in which by correlating information across devices, we can capture rich information about users' behavior, intent, and context to enable new interactive experiences. To go beyond the simplistic approach of using touch and type on a small piece of screen as was the primary way of interacting with information. So for future work, I'm trying to extend the current focus from the input side to the output side, in which case I try to consider and ponder about how digital information can be presented to the users. And in particular, I want to bring this information away from the screen, going beyond pixels, and instead bringing this information to the physical world. So to do that, I'll drive 3 areas of research in the future. The first area is cross-reality interaction, which means we want to interact with digital information not just on the screen, but in the wild, in the physical world. Another way to bring digital information to the world is to turn users' design ideas from digital artifacts to physical objects. So this requires research on expressive design and fabrication. And finally, I want to look at the area of wearables, in which I imagine this is a way of extending the pixels from the screen to the user's body, which can also augment users' certain capabilities and their experience. So for cross-reality interaction, Disney has shown great interest in this domain by enabling drawing to come to 3D alive. This more recent project, a magic bench that have people sitting together with virtual characters. And this area is still posting a number of interesting ACI questions, from looking at improving the existing input that consists primarily of voice, gesture, and gaze, how to improve this existing paradigm. For example, incorporating our devices as mobile and wearables. We can also look at how we can enable navigating, placing, and retrieving information, not just on the screen, but in the physical world. Or enhance awareness and shareability between users, going beyond their individual, isolated virtual world to keep each other aware and information shareable. And I want to focus on this second topic, in which I think mobile and wearable devices first really create a way for enable physical affordance as virtual tool. So imagine you can take your phone, which becomes the handle of a weapon used in a video game experience. Or as an artist, you can use these physical devices to switch between different tools for artistic creation. And you can even go beyond phone and wearables. You can take arbitrary physical objects, using them as surrogates to enrich how you can specify what you want to do in the digital world. We can also think about enabling seamless transitions between the screen and AR projected real world. So this is a scenario imagine that could happen in which the user swipe on the screen and virtual character jumps off the screen to the physical world, and the user starts carrying a story that would guide the character to maneuver in the physical world in response to the user's storytelling. And the research questions here are in terms of sensing, how to track devices, gestures, environment to achieve such seamlessness of transition. And in terms of interaction, how to explore a mix of modalities to drive the characters and stories. For example, using speech plus gesture-based direct manipulation. Expressive design and fabrication. So in order for users to bring their ideas to the physical world as printed or fabricated objects, we need to overcome a number of problems that already exist, such as designs already projected onto a 2D screen and lack a express representation. Interaction is limited to very basic mouse or touch input without expressive ways to specify what users want. And users also need to go through very low-level geometry creation rather than specifying their goal at a high level. And finally, the design process is almost entirely virtual due to the lack of support for physical exploration. So by tackling these existing HCI problems in design fabrication, we can achieve software, can provide software or hardware kits for people to create stories. So first, we can create stories from physical means to digital forms. For example, this is a way of creating stop-motion stories by first handcrafting the character and then manipulating the character, capturing the motion and the storyline into digital form. And the research question here is in terms of hardware, how do we provide custom devices to support the creation and manipulation of these physical characters? And on the software side, how can we provide design tools that can guide users who are non-expert in animation to compose, capture, and edit these stories? We can also go the other route, which is from digital to physical. And these can involve turning users' digital drawing to 3D representations, such as a kit they can assemble together to experience what it's like to have the drawing become actual physical scenes. And the research questions here is, for software, enabling user input to improve the process of converting 2D freeform drawing to 3D physical models. Or on the hardware side, adding more customizable sensing interactivity modules to turn the previously static stories to a live version of it. The last area I'll talk about is augmented wearables. So imagine in the future, wearables can become more comprehensive in sensing and interaction. So this is a Mickey Mouse wearable head, and that has multiple interaction modules. First, it has an actuation mechanism that can animate the ears, which will allow users to add expressiveness to certain body parts. And the research question here is, how do you have users control these ears, as most people do not know how to move their ears by nature? Another feature here is a camera that can sense users' hand gestures. So the research question here is, how to capture users' gestures in a physically visible way, and also provide input vocabulary for them to express to the device. And finally, we can also have an array of actuators to provide tactile feedback on this wearable. And we can really explore what types of feedbacks are possible and how to integrate such feedback into the existing digital experiences for the users. So I just talked about 3 research areas for the future I want to drive, and all of them can have overlapping area and questions with existing research in Disney, which I'm really excited to collaborate with people here and tackle certain problems in combination with my HCI focus. So that concludes my talk. I'm happy to take any questions.